Good morning, my hydroxocobalamin metabolizing youngsters. Welcome to Crystal Chemistry. One of the things we can't do are experiments while we're not together. And so I needed a way to bring this alive a bit more, like I've done with the magnetite finger painting and other stuff. And pictures are one of the best ways to do this. So if we can't do an experiment, one of the things I can show you is how you can see the world differently. And again, please don't think I'm trying to be like, all pompous and I want to give you new eyesight. But what does a music teacher do when they teach you notes? They give you new eyesight. You can look at the notes and hear a song. When you learn to read, I remember the joy of my daughters the first time they said, "McDonald's, I can read that." And then I'd say, "Oh, it's closed." And they would, "Ha, it says open, Daddy." And the joy when you have a new language at your fingertips. And this is what I want you to see when you look at rust, or you look at your mom's engagement ring, when you look at different colors of old metal. I want you to see the language that's being spoken to you here. And to me, this is a great substitute for the lack of experiments. Now, why did I pick crystals? Because crystals are way prettier than powders. Not every formula means it's a crystal. Water is H2O and it may not be in a crystalline form. Obviously, it isn't a crystal when it's liquid. And when it's frozen, a solid block of ice is not the same crystalline state as snowflakes. Diamond is a crystal of carbon, but charcoal is not. Metal oxides are commonly known as rust. But rust is not a crystal. It would be really cool if an old car turned to rubies, but it doesn't because it's not the right heat, temperature, and pressure to make the crystalline form. The most famous crystal, of course, is diamond. And diamond is a crystal of carbon that is formed under great heat and temperature. Charcoal, graphite, plain old carbon soot are not in a crystalline form. Graphite is in a plane of hexagons. That's different. When you get to grade 10 optics, you'll study index of refraction, which is how much is light interfered with when it goes through a new material. And diamond does more to light than any other substance. Light speed actually drops by 2.5 times on the way through diamond, and this will split the light into spectrums, and it'll ricochet around in there called total internal reflection, and it'll come out with a color split. And you'll study this in grade 10. Now I've given you a little preview of that. You really have to see a diamond in real life to watch the light show as you walk around it. Pictures don't do it justice. Most of us will never be able to form big diamonds, so instead we buy rust. Zirconium oxide, when it is in cubic form or in crystalline form, is a gemstone that is almost indistinguishable from diamond unless you've been trained. And it's a mixture of zirconium and oxide. So what do we do here? We look up at your table and we look for oxygen and zirconium. And what you'll find written on the table, zirconium says +4, oxygen says -2. By grade 10, you'll be able to jump to the answer. But if you're uncertain, or I ask you to demonstrate ionic bonding, you would draw zirconium like this, put in the oxygen. If you use Collotti notation, you put the empties in so you're certain of what you're doing. You can demonstrate where the electrons are moving. I can paint their original spot out. You cannot. They'll still be there in your writing. There's insufficient room in oxygen to take all 4 of zirconium's valence electrons. So it requires us to bring another set of oxygens in to pick up these electrons. The formula, therefore, for zirconium oxide is actually zirconium dioxide. And that's what you're looking at there when it is in gem form. If you went into the cupboards at school and we had zirconium oxide, you wouldn't find it full of a bottle of diamond substitutes. Because if such a bottle existed, I'd be on a plane to Monaco with it. What you'd see it in is a powdered form, a non-crystalline form. Just like when you have your pencil, it has the ingredients to be diamonds. It doesn't have the correct structure to be a diamond. You know this to be zirconium dioxide. If it was CO2, you'd call it carbon dioxide. Guess what trioxide, monoxide, pentaoxide are? Do you really need me to write those down? That's in grade 10, but sometimes I kind of go like, I think most kids know what trioxide would be. Pentaoxide, hexaoxide. Salt! Salt has a crystalline form, and we usually leave it in that form. And have you ever noticed all the boxes of salt say Windsor? The salt mines are right under my house, thousands of feet down, huge caverns. And the symbol for salt is Na, or for sodium is Na, which is natrium, a place in Egypt that sort of picked up the name for it. Stop writing sodium as S. Stop writing sodium as S. Students do that all the time. What's this iodized on the box of salt? Conspiracy theory galore. People are getting sick in Bangladesh because there's a rumor going out that iodized salt is a poison. We'll see later why they put iodine in salt. There's salt in its crystalline form. Unfortunately, they don't get very big, so it's kind of hard to make really impressive crystals with salt, which is a shame because the stuff is everywhere and it's harmless. You look up sodium and chlorine on your table. Your table will give you these two values. Oh my goodness, how hard could this be? We'll draw it like that. Many textbooks would simply slide the sodium over so there's an overlap, but you don't see the construction in that form. Now this is where it gets really cool. Sapphire is aluminum rust. It's aluminum oxide. You probably thought aluminum doesn't rust. It does, but it rusts in a very airtight, super thin layer over the aluminum, which gives it that dullish color. If you take a piece of aluminum and polish it, you can get it bright for a moment, and when you stop, it'll dull briefly. I've probably done myself harm that my father had lots of lead and mercury around the house when I was growing up because they used it in the construction industry. And I discovered if I took a block of lead to the wire wheel and polish it, the lead would shine really bright and seconds later turn dull again. And I'd spend hours grinding this lead, watching it get bright and dull because it oxidizes on the surface, and the oxide is like saran wrap. It stops any more air from getting through and the rusting stops. And you get the impression that that metal doesn't rust at all. Iron rust, though, is like sugar coating. It just scrapes off and lets more air in. So how do we write aluminum oxide as a formula? And this would be a grade 10 one. We would definitely want you to do this odd-even split. You go to your table, you look it up, and you see aluminum says +3 and oxygen -2. I have a video on this. You can go watch the video to see how you do odd-even splits. I'm not going to recap it here. It takes too long. What you'll find is the only way you can do this is 2 aluminums would give you 6 electrons and 3 oxygens would give you 6 parking spaces. And the end result is that's the formula for sapphire. If it is cooked under pressure, it's like a metamorphic rock in a volcano. Ordinary aluminum oxide is not this pretty. Otherwise, I'd be going around exposing aluminum to air, scraping off a layer of sapphire, doing it again. If you put the tiniest impurity in the sapphire melt while it's developing, like chromium, you get rubies. Isn't that cool? The opposite end of the spectrum from just adding some chromium. If you decide to major in geology, what this formula means here, this colon chromium, meant that while it was molten, you added some chromium metal. That would be like writing coffee, colon, sugar. You've mixed them. They're not bonded. They were simply mixed together. This is not high school chemistry, but that's all that means. And guess what? You'll probably remember that forever, but if I said memorize it as a definition, you probably couldn't. So one day in university, you might go, oh, hey, I know what that means. Cuprite is copper 1 oxide. Grade 10, mandatory. All this means is we've told you it's 1. Copper 2 means +2. If If you go back to the atomic table in the back of your textbook or the one I gave you, many metals have multiple valence states. Iron has +2, +3. If they want to specify in writing, they put the brackets and then they put a Roman numeral inside. If you turn over your tube of toothpaste, you will see on the back it says tin 2 fluoride. That means it's tin in the +2 valence state. I don't bother testing that in grade 9. It's mandatory in grade 10. In grade 10, we want you to be able to leap to the formula. Here, you only have to demonstrate it to me once, and it's literally going to be something like this or sodium chloride. No harder than that. Oxygen still going, feed me. See, it looks like the Cookie Monster. These two eyes going, nom, 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 nom. Want another electron. Okay, send in another copper. And the oxygen Cookie Monster goes, nom, 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 nom. So cuprite has the formula Cu2O. If we have copper 1 oxide in the back cupboards of science, it's just going to be a powder. I'm going to take a stab that the powder might be slightly greenish because many copper compounds are, but I'm not going to bet you on that. Fluorite, fluorospar, is calcium fluoride. Isn't that pretty? That's one of those colors that only girls can name. I just kind of go, it's bluish, and girls will say something like it's turquoise with a hint of persimmon or something like. If you need color identification, ask your girl. They may be what are called tetrachromats. That'll come back in grade 10 optics, but it looks like girls actually see colors better than males, which explains how I dress. We look these two up. We see this. Oh no, 2 electrons, 1 parking space. It's almost like I chose it to be the exact reverse situation of the last example. Would I do something so deliberate? Oh, what do we need here? A 1 goes parked in. How do we get him parked? Can he nuzzle in there? No. Just, you're going to need another fluorine. And it's done. That's fluorspar. Question becomes, what if there wasn't enough fluorine around to bond? Are you kidding me? Can you imagine if I say, take all of Daytona Beach and all of Wasaga Beach, and we color Daytona Beach red and Wasaga Beach particles blue, and we match them up and go, I wonder if there are any sand particles that didn't find their opposite. You could take a flea fart-sized piece of calcium and fluorine, and there's going to be trillions upon trillions of atoms in each. It's unlikely that it wouldn't finish, but if you were in industry and you did something dumb, like you set the fluorine valve to only half of the calcium valve, and there was a calcium feed line and a fluorine feed line, and you didn't mix them up right, well, at the other end, instead of getting just your powder, you would get this dangerous gas or this pure combustible metal coming out. So, yeah, we tend to want to mix them so they all get used up without leftover. Can you imagine if when your car mixed gasoline and oxygen, if not enough oxygen went into the engine, then pure gasoline would be coming out the tailpipe dripping on the ground? That would be unacceptable. And that's what grade 10 chemistry gets in. Mixing so we use up all the ingredients. Titanium dioxide is going to be an obvious formula. That's it as a powder. This is it as a crystal called anatase or brookite. And these formed under different temperature and pressure environments or regimes, as we would call it. They call it titanium dioxide. Ooh, I wonder what that formula is. It's this. And if we look it up, titanium is +4. It has 4 electrons to get rid of, and oxygen -2. It can take 2. So yeah, that makes sense. 2 oxygens would accept 4 electrons, and titanium has 4 to give. You have titanium dioxide all over your life and you don't know it. That white cream you spread on your nose if you're a lifeguard is a mix of titanium dioxide and zinc oxide in a paste, similar to Vaseline. If you open your car door, take a look for white grease on the hinges. It is very common to use titanium dioxide grease in areas where you might bump into it. The white color is a giveaway. It's a finer kind of grease. It seems to be preferred to use on rubber seals. And if you're ever servicing some equipment, it might say get titanium dioxide grease. Many oxides of metal, not iron, it's gritty, nasty stuff, but titanium dioxide, magnesium oxide, zinc oxides as powders can be mixed with a grease and make a very soothing grease for human skin and very sensitive equipment. If your car's been recently lubed, open the door and look for the telltale white titanium dioxide grease they use on the door hinges. Zinc oxide is the white powder that you spread on your nose, but in crystalline form, zinc oxide looks like this. You would definitely not grind this up and rub it on your face. It would be ouchy. We look it up. Oh my goodness, how easy is that? Right? You can finish that. Come on. 2 dots, 2 empties. It's going to be 1 on 1. Tin 4 oxide. This looks like, I want to taste it. It looks like really dark purple jello, and I look at this and go, I bet you it tastes like grapes. And then I'd be at the dentist with fractured teeth because he would say, why the heck would you try to eat cassiterite? I thought it looked like jello. This is tin 4 oxide. There's another version of it that cooked at different regimes. Now, I definitely wouldn't want to bite that, but this reminds me of some of those Italian, like, pastry flakes. Tin is SN. It's not Ti, that's titanium. SN. The Romans knew about tin. It was called stannum. Stannum, it says +4. So it's 4, and oxygen's -2. However is this going to work? Wait a minute. It's exactly like titanium dioxide, because that's the patterns in the table. Tin is SN. Stannum. Okay? What did the tinsmith say about his hopeless apprentice? I can't stand him! Tin whiskers, tin disease, tin pest, and tin leprosy. Those are odd phrases. You know lead is bad, and I'm probably suffering from lead poisoning from what I did as a child with my dad's lead and mercury in the garage. We've tried to eliminate lead from our environment. One of the areas where lead was commonly used was in solder, the kind of solder for wires and the kind of solder for pipes. If you go to Home Depot, you will see that they want you to buy silver solder. They've substituted the lead for silver for drinking water pipes. Do not go cheap and buy the lead-based solder. It's illegal now. Why they're still selling it, I don't know. Why would a person want to buy the lead solder, not the silver solder? Take a guess. The silver solder is a lot more expensive, and the melting point of silver is much, much higher. The end result is it takes longer to make the joint, but it's vastly safer for the person doing the soldering and the person drinking out of those pipes. Electronics offer a different problem. If you make the solder with a higher melting point, you can destroy a circuit while you're soldering it. However, a problem has emerged. By getting rid of the lead, a behavior in tin came out that was not expected. It starts to crystallize and forming these things called tin whiskers. If you look at this picture, can you tell it's magnified hundreds of thousands of times? And these little tin whiskers, at best, you'd see a fuzz like cobweb around that. This is the gap between 2 pins on an integrated circuit chip. So these are tiny, tinier than pins. And this little tin whisker grew across the gap and destroyed the circuit. We've lost satellites worth hundreds of millions of dollars because of the tin whiskers. It's a growing concern, and they're trying to solve that. And if you could solve the tin whisker problem, wow, you'd be rich. Another nickname for it that was known in the past is tin disease, tin pest, or tin leprosy. This is an aluminum plane, but the tin ones do the same thing. You'd get a tin toy from the 1930s and open up the box one day, and it's just falling apart like it's rotting. And it's a reaction with tin, and it cannot be stopped. Once it gets going, you're screwed. You're going to lose this toy to dust. And you must isolate it from the other toys. If you had a museum of tin toys and collectibles, and one of them started this tin pest or tin leprosy, you got to get it out of there. It will spread to all the others almost like an infection. And again, this is an unwanted characteristic of this metal that Yeah, you might go, oh, my rare toy fell apart. What if it's a $500 million satellite that suddenly stops working? And our mission to Mars, we better be certain before we send astronauts on a multi-million, billion-dollar expedition lasting years that we've solved some of this bizarre chemistry. I can't look at this picture. It's so gross. Putting my hand over the one. Tin 2 fluoride is what's in your toothpaste. It's called tin 2 fluoride, or the old name stannous fluoride, or just fluoride, which I misspelled there. The picture on the right side that I can't look at because I got that kind of hole phobia is what the dentin tubules on your teeth look at, magnified millions of times. And so they're 5 micrometers across. And after you brush with tin 2 fluoride, the tin 2 fluoride crystallizes in those holes and blocks it. And this causes a desensitizing to pain. So this is not normally how it coats the teeth. Those dentin tubules only get exposed as your teeth get older and the enamel wears off. So like my teeth get cold sensitive. So when I brush with Sensodyne toothpaste, what's happening is it's plugging those holes with the tin fluoride, and then you get less sensitivity to pain. You can use a similar setup to block holes in concrete if you've got a slightly wet basement wall. What happens when you drink fluoridated water, which you're kind of moving away from because everybody has fluoridated toothpaste? This is grade 11 chemistry. There's a little hint in grade 10. This whole big cluster here I put in blue is called calcium phosphate. And it can attach itself. It behaves like it's its own element. It's behaving exactly like lithium. It has a single valence electron left when this entire cluster forms. It's kind of like you're hiking and you come across a camp and there's like 20 people having a great camp and you're going to set up your tent by yourself and they come in and say, no, come on in, there's room for one more. So you could just pretend that this is the letter H, and it bonds to this OH that's traveling. So a group of campers meets a husband and wife hiking, and they say, join us. When you brush your teeth with fluoridated toothpaste, this fluorine comes along and goes, get out of there! And it joins the camping group. And your teeth switch from being calcium phosphate hydroxide to calcium phosphate fluoride. It forms this fluoroacetate, which is a rock-hard crystal, much harder than the original coating on your teeth. And this is what's called a single displacement reaction. You will study it in grade 10, both in academic and applied. In academic, they might go as far as this structure, usually not the calcium in front, and not in grade 10 applied. We wouldn't bother with a big structure like this. But it's not hard. But anyway, all that's happening is this little OH is being kicked out for fluorine. It's definitely not high school chemistry. But I know a lot of you could go, yeah, I see where this is going. Hematite, hemoglobin is blood, heme, red. Iron 3 oxide, that's your classic rust. So if you find a rock that's got this reddish patch, really good odds it's iron 3 oxide. Sometimes it can come out a little bit darker. Typical rust, iron 3 and oxygen. It's another one of those 2-3 splits. And that is grade 10. Right? I'm not going to bother asking you one of these on a test because why? If you can demonstrate 2 goes into 2, you got the pattern. There's no reason to be crucifying you with the harder ones. Iron pyrite is fool's gold. Now pyrite, there is no pyrite on the table. Geologists name this. It means iron made in fire. Pyrolusite, again, that mineral name like ruby or sapphire gives you no hint. It's known as manganese dioxide, and nobody wants to put that on their ring. But you got this by the pounds in your life. It's in all throwaway batteries. Which one of these would require 2 oxygens? Manganese when it has 4, or manganese when it has 2? Which one of these states of manganese would need 2 oxygens? Well, 2 oxygens would be that. So yeah, there we go. And that's manganese dioxide. I used to get in so much trouble as a kid because I'd pull apart old carbon batteries to get rid of the carbon rods in them, and they would come out all gloopy, covered in this manganese dioxide, which is a black crud worse than toner powder because it's sticky. And I left the carbon rods in a pair of blue jeans that had a zipper on them. And the next day when my mom had put my wash away, I opened up my jeans and found these pristine carbon rods polished beautifully. I was like, this is awesome! So for about 3 months, I kept pulling apart old batteries, taking out the dirty carbon rods, putting them in my blue jeans, so when my mom washed them, I got clean carbon rods. And then one day I hear her complaining to my father, we need to do a washing machine. Everything's coming out gray and streaks of black. And I'm like, uh-oh. And she never found out that I was using her washing machine as a chemical repository for a actually carcinogenic powder. Galena, lead sulfide. Galena used to be played with a lot. We don't play with it much anymore. Lead is PB. It's plumbum. And we still use the word plumbum as plumbing and a plumber. Basalt. This is in Ireland, the Giant's Causeway. Go walking there one day and think of me. I just think of Nicolati drowning at sea for all the work he give us. Basalt is the most common igneous rock on Earth, and it's a mixture of silicon dioxide, titanium dioxide, magnesium oxide, calcium oxide, and aluminum oxide. Hey, wait, isn't that sapphire? Yeah! And so that's what those people are sitting on. They're sitting on chemistry. Isn't that pretty? Millerite and hazelwoodite. These are both nickel sulfide. This is nickel when it's in its +2 state. And this would be this is -2, I know that. So if this is -2 and there's 2 of them, it's -4. Oh, dang. What times 3 is 4? Which one of these can you do and which one can you not? Like, you can only do one of these. Okay, that's sulfur. Oh, I can. Which one can I do? Which one can't I? And the last two that get really complicated is fuck-you-cholite and dickite. And these ones are chemistry beyond me. Like, I have no idea how to do fuck-you-cholite. Like this mess here, I know I never studied that. So, fuck-you-cholite, no. Dickite, no. So, this would be where, like, it's beyond my chemistry. I can't do nothing with fuck-you-cholite and dickite. So that's where I'm going to end crystal chemistry, with fuck-you-cholite and dickite, because, like, just to show you, like, teachers don't know everything, and I bet you I'd stump any of the high school teachers with this, because we don't do geology. So fuck-you-cholite and dickite, you're on your own with. And then later I'm going to move into the ones on this side of the table and show you the mysteries of the covalent crystals. Anyway, it's a poor substitute for some really cool labs, but I thought I would try to do a little